Hello guys, this is Subhrajyoti again, and today we have the earliest group, or we can say from where we have started, cosmic conversation members we have today. Today Shivam and Prayog has joined. So Shivam, over to you now.
All right. So we have Prayog on the panel. I welcome you, Prayog. बहुत बहुत स्वागत है आपका. So Subhrajyoti and Prayog. First of all,
yes,
how do you feel about the cosmos, or we can say the universe?
Cosmos. The name itself is exhilarating. It's a thrill. It sends chills to the bones. Okay, means it is very deep and mysterious and amazing. The more you go, the more you realize how less you know about things, that how things work. So it's a wonderful journey, even if it is baby steps to know how it all works.
Obviously, मतलब बहुत अच्छी चीज है.
Okay, for me, Cosmos is everything. Means my account name is also
Even your
Cosmos, but
username, even your
हाँ,
username.
उसमें बस O की कमी है क्योंकि that time I think I don't know what Instagram wanted. That time O I could not add.
It was taken. That's why Instagram
Yeah.
suggested another
So
username.
So no, I have cut that O and then it has shown green signal. Okay, go for it. So yes, now we are okay.
जितना तुम कॉस्मोस के बारे में जानोगे उतना तुमको पता चलेगा कि तुम कितना कम जानते हो दुनिया के बारे में. So without any further ado, let's jump right into the topic, that is the neutron star, the weirdest thing ever possible in the universe, except black hole. So so what makes neutron star weird, and the function, structure, and origin, all that stuff we will discuss here today in this podcast. So bring your popcorns and your Coca-Colas. Let's start this journey to the amazing neutron star.
The story about neutron star, or the story of neutron stars, started from, like, everything has started because of the birth of the universe, obviously. But प्रयोग और मैं, yes, आप लोग भी जानते होंगे कि stars जो हैं, the stars, or we can say the hydrogen clouds, in the beginning of a star, there are hydrogen clouds which combine together due to the strong attraction of gravity, and due to the pressure, they start the nuclear fission in their core, and then a star has evolved into, Prayog, if I'm not wrong, it has to evolve into a red supergiant, right?
Hmm.
So, Prayog, as I said,
Yeah.
a star has to gather a fixed amount of mass, or a mass over a limit, which is, do you know what it is? Subhrajyoti.
Yeah.
Subhrajyoti, tell me, what
That
is
is a
that
secret
limit?
limit.
Exactly.
Yes.
A
I
star
think
has to.
you are not a teacher. Only I thought that it's a classroom-like feeling. Shivam is my teacher, and I am sitting like this, watching him, and he is asking me question. Throwing
No, we
notes.
have to make it
What is
interactive.
it?
That's why.
Yeah.
Okay,
Yeah.
a star has to over that limit in terms of mass, and when a star collapses in a supernova explosion, we have made a video about, we हमने इन सारे events के बारे में video बनाया है, आपको Instagram पे मिल जाएगा, links description में हैं तीनों के Instagram के. So the thing is, there is an object, a type of object which we are going to discuss today, and it is neutron star. A star which is completely made up of neutrons, or the neutral particles in terms of charge. Prayog, I would like you to begin the story of how a neutron star forms.
So all this started with a man, an Indian physicist, Subramanian Chandrasekhar, who asked the question that how big a star needs to be so that it can balance off its own mass against gravity, even after using all of its fuel. So this question led to ultimate result of neutron star. Means neutron star, from this question to neutron star journey, it is long and it's also exciting. Okay, so I will narrate it. You just sit back and relax. So what happened is, okay. So what happened is this guy Subramanian Chandrasekhar, he was at Cambridge, and he asked this question because of a principle, that is the Pauli exclusion principle, which basically said that two particles cannot have same quantum state. They may have similar quantum state, but they must not have same quantum state. So what happens is when two electrons try to come closer and closer, try to acquire the same quantum state, the Pauli exclusion principle rejects that, and the electron starts giving off a pressure which is called a degeneracy pressure. The electron becomes degenerate matter, and this pressure is called electron degeneracy pressure. So because of this pressure, the star can balance of the gravitational attraction, and it can not ultimately collapse into a black hole. Okay, so
और यहाँ जो इलेक्ट्रॉन डिजेनरेसी प्रेशर की बात हो रही है, if you don't know, I am talking to the viewer, you don't know what star it is exactly happening. So it's the white dwarfs. और अगर आपको इसके बारे में जानना है, अगर आपको चाहना इसी वीडियो में जानना है इससे पहले, तो आप देख सकते हैं, वो लिंक्स वगैरह पड़े हुए हैं हमारे, मेरे को प्लग करना जरूरी है.
I know.
So Prayog, now continue.
Okay, so exactly what Shivam said, that these stars later came to be known as white dwarfs. Lev Landau, another Soviet physicist, came up with a different conclusion. He said that there might be another possibility to quantum degeneracy pressure. He said that a star nearer to 1.4 times mass of the sun can collapse and balance of its own mass against gravity by the pressure exerted by neutrons. So this is called the neutron degeneracy pressure. Okay, this Soviet physicist, great pioneer in condensed matter physics, okay, Lev Landau, he came up with a different possibility for the ultimate fate of the star. Okay, so he said that the star can balance off its own mass against gravity by neutron degeneracy pressure. So what is this neutron degeneracy pressure? Okay, so as stars are coming closer and closer, more and more, so this, not even electrons, now neutrons are trying to acquire the same quantum state. Again, the Pauli exclusion principle is rejecting that. It is against that. So these neutrons are starting giving off a pressure which is anti-parallel to gravity, and this is indeed expanding the star from inward. And this star later came to be known as neutron stars.
So this is the basic question. The basic question was, what will happen if the star gets contracting and collapsing into itself? What will happen? And the end result of that, not the end result, but yeah, next to the end possibility, or the second next possibility, is a neutron star. Yeah. That's what Prayog explained beautifully. Thank you, Prayog. Okay, Subhrajyoti.
Okay, so if you think, means if a sun-like star is there, then it will go through different processes, and at last it will become a white dwarf or anything. Theoretically, that scientists have assumed.
Yeah. It is predicted that it will end as a white dwarf.
White dwarf. But for a massive star, things get more interesting as their helium get exhausted. If their helium get exhausted for a moment, the balance of pressure and radiation tips and gravity wins, or you can say the gravitational forces means just is more greater than the pressure.
Has overtaken the pressure released due to the heat of the nuclear fission.
After that, after the gravity wins, we can say a process starts. That is, carbon burns into neon within some centuries, you can assume. Then neon burns into oxygen within some years, you can say. And the oxygen to silicon in some, I think, months. And silicon to the final state, iron, in some days. Okay, you can say one day or some days, you can say. So what is left is, that is iron ash. What the...
an iron core.
Iron core, which you can say that nuclear ash. Yes.
Yes.
So from there, Prayog can continue.
Okay. So now that Subhrajyoti has gone explained what happens to stars beyond 1.4 solar masses, but we'll talk about what happens to stars within 1.4 solar masses. So now we have talked about the origin of the neutron star. Now we can continue about the structure, because the structure and formation. The structure is what makes the neutron star the weirdest thing in the universe. Again, except the black hole. Okay, black hole has no structure, no structure. Nothing is there. There is just a singularity, and there is a sphere, that's where all the information is stored.
You can say that sphere is hole.
Yes, it is. Yeah, I said it. मैं बोल लूँ, Subhrajyoti? I said it. A sphere of darkness. It is. With a singularity or a naked singularity in the core of that sphere.
But that universe happened in neutron star. Neutron star is far more exciting than a black hole, in some sense, in the sense of structure. So we'll cover every bit of it. Okay, there is like a planet which has atmosphere. It has surface, it has crust and core. Same happens in neutron star. It has also atmosphere and all the things that planet has. But in a much different level. Before entering the neutron star, we enter the magnetosphere. We experience the magnetosphere, and this magnetosphere, believe me, it's the strongest magnetic field in the universe. And why? Why it is strongest? Because it is made up of electron and positron pair which are moving around a nuclear neutron star in opposite motion.
Direction.
Okay. In
Hmm.
opposite direction, yes, in opposite motion. So, and from where this proton and electron and positron came from, it came from the photon in the magnetic field. So this photon is ripped into electron and positron, which move around a neutron star, produce a magnetic field, and this magnetic radiation we observe as pulsars.
Exactly.
Yeah.
Yep.
Yeah. So the thing is, Prayog, do you want to say that a photon, okay, a photon is what do you say that is decayed
Ripped,
into an yeah
decayed,
It is
decayed.
decayed would be a gentle word. Okay, so it is decayed into an positron and an electron pair, which is antimatter matter pair.
Hmm.
Yeah, it is.
So
So
yeah, it is theoretical. Okay, again, it is theoretical.
theoretical help.
It is may be observed in the LSE. They have this huge magnet that they may have observed that. But as far as I know, all this thing is perfect and theoretical about the motion of a neutron star. And you may also ask that why this and if this positron and electron pair collide and they form a huge burst, it does not actually happen often. It does not really happen actually because the motion in which they are acquainted is very precise and not very jumbled. Okay, so that is why they don't actually collide. Right. So now that we have covered the magnetosphere, now let's jump into the atmosphere.
which is
This is
a
where the
centimeter
begins.
thick.
Which is just yes,
it's a meter thick, 1 meter thick.
1 meter.
Okay, it's a consider now.
Not exactly even a meter.
It's almost a meter thick, means around average neutron star. It's a meter thick atmosphere, and in compared to Earth, it is 10,000 kilometers thick. The atmosphere of Earth it is 10,000 kilometers. But this our atmosphere is made up of gases and atoms, but the atmosphere of neutron star is made up of plasma. And this plasma is like a thick cell. It's around 10 centimeter. Around it is like a blanket of the neutron star. You can say. Okay, it is just 10 centimeter. Very thin cell, but very dense. It is made of plasma. Now that we have covered
For
the
example,
atmosphere,
for example, it is like it is the length of like this bit. It is equivalent to that.
Yes, yes, it is 10 centimeters. Yes, it is precisely 10 centimeters. Its line is 10 centimeters, and yes, this much only the plasma layer. So
Subhrajyoti
now
is trying.
atmosphere.
Subhrajyoti
This
is trying his
This
best.
line is best to show the demonstration.
Okay.
Yeah, that's what it dedicated
I have
teaches.
got a pen. I have got a pen. I have got a pen.
Finally,
Finally.
so now after this atmosphere, then comes the surface of the neutron star. Surface of the Earth is soil. The surface of the neutron star is iron in crystal lattice form. Okay, so the salt is in crystal. Many things are in crystal. So this iron, it's a new thing. The iron itself is in crystal lattice form. Okay, so you may ask from where this iron came from. So this iron is the leftover of the supernova explosion. So a star has an iron core. So this after in supernova the star implodes from inward burst. The iron is spilled out and it forms the surface of the neutron star.
The implosion, that implosion part, let me say, is due to the gravitational force which happens at a speed of 25% at the means 25% of speed of light. You can say means nearly or around it. That number, exact number is 25% of the speed of light. And then after I was telling the speed because after that a shock wave happens due to which it explodes and gives and it results into supernova explosion. By that supernova explosion which shines all over the galaxy, you can say.
And its residue is what Prayog is talking about, which is an iron core which will later transform into a neutron star.
Mind-blowing fact I want you all to look up is that that leftover mass is just 5 kilometer square. I think its volume is 25 kilometer cube. You can assume means it's near around that. So its mass is the million times of Earth. Means you can imagine how, means I'm telling the numbers how much it is. So it is so much dense. I was attending the I was gaining back the attention of the audience through these numbers. Okay, so let's Prayog.
After surface comes the crust. Okay, so this crust, outer crust, means the crust is divided into 2 to 3 parts. So this outer crust, 100 meters below, and then the inner crust. So the outer crust of a neutron star is where this Fermi degenerate Fermi gas or degenerate gas of electron lies. Okay, so they prevent the star from further collapsing. This is what the magic happens. So they say that neutron star is completely about neutron degeneracy pressure, but actually it's no. Up to some point, electron degeneracy pressure also plays a little bit of role in preventing the atmosphere and the magnetosphere and the surface of the neutron star to crush. So this is the role of the gas of electron or the degenerate Fermi gas. Okay. Uh, so now after this, it gets denser and denser and hotter and hotter. So the atoms become so close that the electrons are forced inside the nucleus of an atom. This iron atom, which is the iron element. So the electrons of iron and the heavy elements are electrons of this and are forced inside the nucleus. This process is called electron capture. So in this way, the negatively charged electrons and the positively charged protons make more neutrons, and eventually they form elements which are as heavy as iron but more neutron rich. Okay.
So now, after as I said, the crust is divided into 2 to 3 parts. So after the crust, there comes 100 meters below the surface, where the density of the star is 50 billion times the density of Earth. So now we start to find atoms like zinc 80, and there will be more atoms. You can see this picture. Okay, as we go deeper and deeper, we find more, as I said, more neutron-rich element, but just as heavy as. So after encountering the outer crust and 100 meters below the crust, it is not the last part of the crust. It is the inner crust, and in the inner crust of a neutron star, it's about half a kilometer deep, and we start observing a process which is called neutron drift.
So the inner, you are talking about the inner core. So I would like to give same
inner crust.
I would like to give
crust,
a picture.
Yes.
Inner crust. I would like to give a picture about it. Means there are three. Means as you come down to it, there are 3 phases you will face. I think the gnocchi phase, the spaghetti phase, and the last. I think
lasagna
I cannot
phase.
pronounce.
Lasagna phase, yeah.
The last two phases, you will see a nuclear pasta, which is the hardest, or you can say means yes, it's the hardest matter or party. Okay,
Material
Material in
it's
the
the hardest
universe.
material in the universe.
So guys, I know you are somehow lost in this podcast. खो गए होंगे आप क्योंकि ये काफी ज्यादा messy है और we know it. ये एक arranged script के through वजह से नहीं हुआ है, and you know how podcast works. So अब हम यहाँ पे conclusion देने वाले हैं थोड़ा बहुत कि हमने अब तक क्या बात की है. ये अगर आपने वीडियो नहीं देखा होगा तो आप समझ जाएंगे. So Subhrajyoti, now begin with the conclusion of the whole podcast.
Okay, till now I think Prayog said about all the means from the origin of the neutron star to the crust, up to the crust. Yes, up to the crust. Yeah, the means Prayog, or not only Prayog, Shivam and maybe I have all said or described about this part. So in the next part, we'll obviously go more deeper into it, and then okay, now Prayog.
So we have explained in the utmost detail about until the inner crust of a neutron star. What comes next is what makes the neutron star weird. That is the reason why neutron stars are weird, because it has taken lots of years to figure out what happens after the crust. उतना तो प्रेशर और टेम्परेचर में ठीक है, थ्योराइज पार्टिकल हो सकते हैं, बट अभी प्रेशर और टेम्परेचर इतना बढ़ जा रहा है, ग्रेविटी इतना डेंस हो जा रहा है कि क्या भाई क्या निकलेगा. So
it is unpredictable yet predictable.
Yes, it is means different things what might happen, what might not happen. Yes, it is completely theoretical, and it is sometimes probabilistic. But it is not accurate that we may find this stuff inside a neutron star if we someday, sometime in far future, if we go to search.
If we get a chance to study a neutron star,
studies
or its core
practically, which is
we may not find the exact thing. We may not find the exact things, the exact theorized stuff inside its core, but it's highly probable that we'll find stuff which we are discussing here inside the cores of a neutron star.
So guys, stay tuned and wait for the part 2, and it's gonna be lots of fun. Bring all the snacks and sit and just enjoy the video. Slow down your speed, the playtime speed, because it takes a lot of time to get this material, because it obviously took us a month or so to absorb all this stuff, and we are passing it on to you in just 40 minutes or 20 minutes long video.
That being said, we would like to end this
Today's
episode.
podcast.
And in the end, wait, Prayog, thank you for being here, and thank you for being so helpful to the audience, and thank you for enlighten us with the knowledge that you possess.
Thank
Stay
you.
tuned
No,
on Astronomer
it's a
Says.
pleasure. Okay. Uh-huh.
Yeah. Stay
Thank you all.
stay tuned on Astronomer Says. Have a good